Okay, good evening everyone and welcome to the fifth session of the course Dynamical System and Control. Today we'll be seeing some uh, stability notions of a system of differential equation, and we'll see the notion of phase portrait and phase diagram for the solution. So to begin the session, let's start with some definitions. So consider this system y prime equal to fy. So this is a system of first order differential equation, and here this f function f is not depending on time. So we are in a system of which is called autonomous system, right? So we'll be dealing with this kind of system, and we say that the solution curve, okay, so the solution curve of the above system can be defined in this way. So it's basically what you have seen for functions. So it's nothing special. So you know that this y, the solution of this curve is a map from R to Rn, right? So it has n components. So it's basically a map which is taking the value from real number and it is mapping to a vector in Rn, correct? So we'll be looking at this map. So this map is use the graph of this map is nothing but t comma and these n components. Okay, so this vector in Rn plus 1 is what we call solution curve. Okay, so the solution curve is given by this set. Okay, and now we'll be looking at the orbit of the solution. In orbit we omit this t, so we just look at the projection on this Rn. Okay, so and this plane Rn is called, sorry, this plane Rn which contain these points are is called the phase plane. Okay, so we'll see what these notions are more precisely in some examples. Okay, very soon. Okay, so like let us see this what these notions mean. uh, how to calculate this orbit for a system of first order differential equation. Okay, so suppose we are in the case when n is 2. Okay, so this we are dealing with R2. So consider this system dx by dt equal to fxy and dy by dt equal to gxy. Okay, the solution curve of this is basically the orbit. Okay, now what we have to worry about that we should not consider the equilibrium point. Okay, so what equilibrium point means, that basically which is not depending on time. So let me first rewrite. So x naught y naught, or let me write with t. So okay, so it is basically independent of t. The x naught y naught is equilibrium solution. Okay, so it's like xt comma yt. Okay, these are the constant solution, is called equilibrium solution if your f x naught y naught and g x naught y naught is 0. Okay, so this is what is called equilibrium solution. Okay, or critical solution, whatever you say. So a solution curve of the above system represents an orbit provided, I mean we are not dealing in, so this thing is meaning that the solution does not contain the equilibrium point. This is what it means, contain equilibrium point. Okay, so you have to solve this system. Okay, and solving this system will give me this xt comma yt, which is the solution curve, correct? Okay, you can take t also, since here I defined solution curve with t. So consider this set in R3. So this solution curve is called orbit. Okay, if it does not contain any equilibrium points, so that it will not vanish anywhere, correct? And if you know the equilibrium point, so if x naught y naught is equilibrium point, then you know that xt equal to xt comma yt, this set, if you look at, this is nothing but t comma x naught comma y naught when you consider the constant solution or the equilibrium solution. So this is the set, right? So this is just a constant line along t axis. Okay, so these are anyway these as a point. So if you consider it as a diagram or as a plot, so suppose this is x, this is y. So if you increase the value of t Okay, whatever value x naught y naught, suppose it's here, then this is what this set is representing. So the solution curve corresponding to this equilibrium solution is just this a straight line, right? So each of the points, so suppose these are the critical points or equilibrium points. In that case, the orbit is just these lines. Okay, but when it is not an equilibrium point, that means it will depend on time, and that will be one orbit. Okay, so each equilibrium point is a single orbit, and other than equilibrium point you will get a solution. So this will now know. So if you forget about this t, so if you forget about this t, this is just a fixed point. But when this xt yt is not an equilibrium solution, you will get a curve, and that curve is called orbit. Okay, and instead of this straight line, you will get something as a function of x and t, so something whatever you get, but not a straight line. Okay, and this will not contain any of the equilibrium point. So I mean, it should be away from this line. Okay, so these are the orbits. This is the definition of orbit. Okay, so for 2 I am saying, when n is equal to 2, then this is the simplest representation we can have. And if you want to, so this is one way of saying that what orbit is. But if you look at this one, this 2 equation, now if you divide, so dy by dt, so this dy by dx can be written as dy by dt upon dx by dt. Okay, but the, I mean, you can assume this as of now, but if you want to rewrite it, write it properly, then it would require invertibility of dx by dt. Okay, it's not that straightforward. But since we are ignoring all the equilibrium points and we are assuming that the solution is very smooth and all, so we can assume that okay, this we can do, that we can divide dy by dt by dx by dt, and when you divide this, you get f of xy and g of xy. Okay, so this, if you can solve, so here from here what you do, it would be more clear by example, but over here what you can say is that when you solve this equation, you will get, so suppose this is from here you will get something xt and you will get yt, like solving this. Okay, now when you solve this, this is nothing but, if you suppose you got xt equal to et and yt is also et or any function, then from here you get x equal to y, this kind of relation. Okay, so to draw this figure, okay, so what we'll be mainly concerned about is the phase diagram. Okay, so will not be considering this t axis at all. So this t axis, what I was telling you, we won't be considering at all. So that means we will be on r2. Okay, so in this plane, so you just have to, while when you get the solution of this system, you will get as a function of t, but you will try to write it as a function of x. So you can write y as a function of x. So in this case, you know that y is equal to x. Okay, to get the diagrams, at what diagram I'll get, this kind of thing. So if y is equal to x, you know that this is the diagram or this curve. Okay, so instead of solving this independently like this, you just try to solve this system, this equation. Now you get one equation, and if you can solve this, what y as a function of x, what you get, then that you are done. Okay, so you can, instead of getting the explicit solution, you can solve in this way as well. So this is an alternative approach to get the orbit. Okay, so we'll see the through the example. Okay, so let me state few examples. So consider this system. Okay, so you have x prime t, so here it's t, x prime t equal to x, y prime t equal to x minus y. Okay, so let us first try to calculate using this one, that we'll try to solve to get the solution curve as x equal to xt and y equal to yt, and in the second approach we'll try to solve it in this way. Okay, then see what the difference come up. Nothing will be different, but there are two ways of doing the same thing. Okay, so before going to solve this equation or system, let us try to find the equilibrium points, right? Because we need to consider equilibrium point, because you see here that this equilibrium point has to be considered separately. Okay, so let us first try to look at the equilibrium point. So equilibrium point is nothing but x naught y naught is equilibrium point if dx by dt, or let me write this, f dx by dt is equal to f of xy and dy by dt is equal to g of xy. If f of x naught comma y naught is equal to g of x naught comma y naught equal to 0, that means both the things should vanish. Okay. So in this case, if you look at this, then this equal to 0 implies that x naught is 0, and if you substitute it here, you will get x minus y equal to 0. This would mean that y naught is equal to x naught, which is equal to 0. Okay, when I solve this one, so from here we know that x naught equal to y naught, which is 0 comma 0, is the equilibrium point for the above system. Okay. So we got the equilibrium point. Now let us try to solve this. So we want to, what do we want to find? We want to find the solution, okay, orbit or the solution curve. Okay, so you see what the, so for the people who have joined just now, so orbit is just the curve traced by these solutions. Okay, that is what we call orbit, I think. And the solution curve is with t. Okay, so if you include t also, like graph, so this is nothing but graph of yt. Okay, so this is solution curve and this is the orbit. Okay, so we have to find the orbit. That means we have to find what is x1t and x2t. So basically the solution is what. Okay, so let us try to solve this first one because there is no coupling, so we can easily solve this one. So the x prime t is given by x. Now if you solve it, you will get xt is equal to exponential of t. We have done this kind of calculation a lot, so we, and then we'll add x, so x0 times et. Correct. Now in the second equation you have y prime t equal to x minus y. Correct. So we can write is y prime t plus yt is equal to xt, and we know what the value of xt is, so we'll just substitute it. So it is x0 times exponential of t. Now let us multiply by exponential of t, then the left hand side would be d by dt of yt times exponential of t, and this is x0 times e raised to power 2t. Correct. Now we'll just integrate with respect to t. So what we get is yt et is equal to x0 e raised to the power 2t, and then plus some constant, but when we put t equal to 0, we'll get y0 minus x0. Correct. Let me see. So if put t equal to 0, this will be cancelled. So this is the solution what we get. This is the explicit solution. Correct. So this can be rewritten as yt equal to x0 e raised to the power t plus y0 minus x0 e raised to the power minus of t. Okay, now you have this expression xt and you have this yt. Okay, now so the solution curve is t, xt and yt. Okay, if you want to plot, you can plot it, what the solution would be. So and so this would be called the solution curve, right? But what we have been asked is to calculate the orbit, so you can forget about this axis. Okay, now you have to plot it in x and y. Okay, that means you have eliminated the role of t. So for doing that, we have to write this x and y as a, so one as a function of the other, right? So you can clearly see this xt is given in by this formula, right? So you have to eliminate t from here. Correct. So to remove this line t, you have to write this xt and yt as a function of each other. So we have to eliminate t if it's possible. Okay, so over here we can see that this exponential can be written as a function of x. So here we can substitute this et by x, correct? So using 1 and 2, we have y is equal to, so here we can simply write x plus, here we can write y0 minus x0. Okay, and e raised to the power minus t can be written as 1 by x. So here you can write 1 by x0 into xt, correct? So I mean these are basically constant, so these are nothing but some constant. So let me write this x0 here, get 1 by xt, correct? So this can be rewritten as y as a function of x. You can write it as, let me write in small, so you can write y as a function of x as x plus some c times x, 1 by c times 1 by x, right? So this is the orbit. Okay, so this is called orbit, correct? So we have removed the t axis, or graphically it's nothing. So when you plot t and x and y, so as a function of t, now you just project it on x y plane. Okay, that is the this orbit. You just project the solution curve on the xy plane, you get the orbit. Okay, okay, so this is one way what we have done in this process, that we have solved it independently. I mean x prime t and y prime t, as a function of t we solved, and then we saw is if there is some relation between x and y. Okay, the other way what I pointed out is you just do this kind of thing. So dy by dx you write it as dy by dt upon dx by dt. Okay, or which is nothing but x minus y upon x. So this kind, now you just, now there is no involvement of t here. Now you can solve it and then you get the solution. Okay, so let us try to see. So this is what we have. So this is another way maybe. So, okay, this is another way. What we have is dy by dx is this x minus y upon x. So this is 1 minus y by x. Okay, so here we are not considering the equilibrium point. So I mean here we are assuming that x and y are non-zero. That's why we can do this division. And okay, so here note that x y is not equal to 0 comma 0. Y you can take at 0, so I'm not just taking this pair. So y can be chosen as 0, but x has to be non-zero. I mean both cannot be simultaneously 0, that's it. Okay. Okay, so over here you just assume that x is non-zero, because we are dividing it, that's why. So then we can write dy by dx plus y by x is equal to x, right? And okay, or you can just directly do this way. So from here only you can write x dy by dx is equal to x minus y, correct? Yeah, so if x is 0, now from here you can see one thing, that if x is 0, then you will get y equal to 0. Okay, so if x is non-zero, that means y is also non-zero, and hence it is not an equilibrium point. Okay, so this is just a remark. So now from here what you can do is you can take y here, so x dy by dx plus y equal to x. Okay, and then you can solve this x dy by dx minus x equal, sorry, you can rewrite this as d by dx of uh, y into x. So x times y, right? If you do this product, if you use the product formula, you'll get 1 times y plus x times dy by dx, correct? So this is what I have written it here. So this is equal to x, correct? Now if you integrate with respect to x, what you get is xy equal to x square by 2 and then plus some constant c, and this will give you yx equal to x by 2 plus c by x. Okay, that means, okay, so I think here is some calculation mistake. Okay, so here you see, here I'll get 1 2 as well, because if I integrate it with respect to t, I'll get here 2. Okay, so here it will be 2 upon 2, and so here I'll get x by 2. Okay, so you can clearly see that in both the cases, okay, in both the cases we are getting the same thing, and this is the what we should expect also. So these are the two ways, whatever suits you depending on the problem, you can use according to your convenience. Okay, so this is how we can obtain this solution orbits. Okay, now for the solution curve, you just need to write this t comma x0 et comma this whole thing yt. This is the solution curve, t belonging to t greater than 0 or t greater than equal to 0, whatever you say. Okay, since we are in OD, we can even write t belonging to R. Okay, because the solution will exist for whole R in this case, because we are system with linear, so it's like y prime t equal to a yt, and we know that here the solution is eta y0 for all t, right? Because here we know that this solution exists because of this linearity. The solution exists, sorry, for all t in R. Okay, okay, so here you can write this. So this is the solution curve, and this is what we have obtained here is the orbit. Okay, if this is clear, then let's see one more. Let us see one more problem. So okay, so this problem I have taken from the assignments. Okay, and why I choose it, because of the following reason. So over here again we'll proceed in the same manner. So here if you see this dx by dt is equal to x square plus cos y, okay, and dy by dt is equal to minus 2xy. Okay, now here you can see that there is a cos function and there is coupling in both the equation. So solving both the equation is a bit tough if you want to solve it, right? Okay, because this is not a linear system because of this cos y. Here you see the product term, so we don't know how to deal with such systems. So again, so what we can think of, okay, let's try the other way. So we had dy by dx. If you want to write, what will be the term coming up is minus 2xy by x square plus cos y. Okay, again this seems a bit complicated, right? We cannot separate it and do integration. Okay, okay, I mean here it might look a bit cumbersome, so here you can even try this way. So dx by dy is equal to x square plus cos y upon 2xy. Okay, now here you can separate actually, so you will see, okay, this is minus x by 2y and then minus cos y by 2xy. Okay, but the problem still remains the same. Okay, again I don't know how to solve it. If you know that you can, if you have idea that okay I can solve this equation, then you can do it directly. Okay, and you can check it, but I could not see any way to solve it. I mean, I could not find any method. If you know something, you can try. Okay, but what I know in the case of assignment problem, that okay I have some options to deal with, right? So we have some options and we can try to solve it, I mean just using the option directly. Okay, so What I did, I just tried using one by one. Okay, so okay, I don't have any extra. Okay, yeah, I have. So let us try one by one. So let us see the first option. Okay, so we have xy square minus sine of y equal to c. Correct? This is what we have in the option 1. So now I'll differentiate it. So differentiate it with respect to t. Okay, then what we have is x times 2y dy by dt plus dx by dt into y square minus sine, the derivative of sine would be cos, and then you have dy by dt equal to 0. Correct? So you can take this dy by dt common from first and the third term. So what you have is y square dx by dt plus 2xy minus cos y dy by dt equal to 0, or you can write it as dx by dt is equal to cos y minus 2xy upon y square dy by dt. Okay, or you can write dx by dy, whatever you want, you can write. Let me keep it as it is. So now we have after differentiating we got such kind of relation. Okay, so if this is an orbit, then this must be satisfied, right? So let us substitute. We know that dx by dt is x square plus cos y, and dy by dt is given by minus 2xy. You can clearly see that these two are not equal, right? So now let us try it with the second option. So the second option is x square y minus sin y equal to c. So here if I differentiate it, I'll get 2x dx by dt into y plus x square dy by dt minus cos y dy by dt equal to 0. Okay, so from here what we can get is 2xy dx by dt is equal to cos y minus x square dy by dt. Again, you substitute dx by dt as x square plus cos y, and this as minus 2xy. You can see there is a bit of similarity, but there is an issue of sign, right? If here I have got minus cos y, then you might have got the answer. So suppose I got minus cos y here, then clearly this will be solved, right? This equality is justified, right? So this is not correct option, but if you see the third option, this is x square y plus sin y, and if you again do the same process, what you get is 2xy dx by dt is equal to minus of cos y minus of x square dy by dt, and which is true. Correct? So this option is right, because here you got minus, here you will get, here if you put minus 2xy, and here it would be x square plus cos y. You can clearly see the equality. Okay, so this option is, third one is correct. Okay, so this is kind of, I mean, just using the option we can get the, I mean, in this particular case. But if you know some way to solve this directly, then you can extract this solution expression. Okay, so if you have any idea of solving this equation, you can try. Okay, but for the purpose of assignment, you can just look at the option, but you should know how to solve this. If you have any idea, please let me know as well. Okay, okay, so this was about the orbits. Now let us move further. So let us look at some properties of orbit. Okay, so suppose you have this system y prime equal to fy. Okay, and suppose this yt. Okay, so this is one remark. So this should also be okay. So here also you can, this is also kind of some point. So here what it says is that if you have a solution phi t, so suppose phi t is a solution of this system. Okay, so phi t is nothing but like this. So phi t is y1t, yn t, correct? So now suppose this phi t solve this system, then phi t plus c will also solve the system. Just because this, here there is no involvement of t in this one, because it is autonomous system, right? So if you have this phi prime t equal to f of phi t for all t in R, because phi t is solution, that means this is what we have, that phi prime t is equal to f of phi t. Now since this is true for all t in R, you can just say this phi prime of t plus some t naught or c is also equal to f of phi t plus c, correct? So for all t in R, because this is true for each of the point t, so if you do this kind of perturbation, then also it is also true, because you can represent this t plus c as t tilde, right? So this you can represent at t tilde, and this also as t tilde, correct? So we have that, okay, if phi t is solution, then phi t plus is also a solution, and this would be required in the proof of this and this, I mean, or maybe one of them. In this it will be required, and here also probably it will be required. Okay, okay, so this is kind of a property what we have, that if phi t is a solution, then phi t plus is also a solution if the system is autonomous. That is important, that this is not depending on t. Okay, this is the main reason of getting uh, such a property. Okay, okay, the second property is that suppose this f function is c1, or in this for more simplicity you can assume that each of the component, okay, have a continuous partial derivative. Okay, that is enough. So assume that this f1 fn have continuous partial derivative with respect to y1 y2 yn. Then in that case, the if you the orbit, okay, will pass through a point y naught. I mean, only one orbit will pass through that point. So if you have this, suppose in R2, suppose you choose some point y naught, okay, then they, from this orbit there will be only one, sorry, from this point there will be only one orbit which will pass. Okay, so y naught, if some other orbit, so suppose if some other orbit passes through this point, that is not possible, or in other words you can say that two orbits cannot intersect. So if you have one orbit, okay, then the other orbit cannot intersect that orbit. This is what this property is saying. So, or here what I have written, that if you have two orbits, okay, then, and which is having one point in common, that means they are intersecting at one point. Okay, then in that case they must be equal. I mean, two distinct orbit cannot intersect. This is what it says. Okay, and the proof is quite easy and you can understand also. I mean, I'll not give the explicit proof, but you can understand what idea they are using. So you know that this kind of condition, this is smoothness condition. Okay, using this you can say that this system has a unique solution. Okay, using Picard's theorem, locally you can say, and this has a solution in whole R. Then also you know that it is true. Now you see that suppose you have this one solution, this is phi t, and suppose the other solution psi t is also there, and suppose this intersect at some point. Okay, so suppose this is psi t naught and this is phi at t1. Okay, and now you can understand, so you don't have to worry about what time they intersect. Okay, the main thing is, so forget about the point for now. Here you just assume what you know, that this psi prime t is equal to f of psi, and this phi prime is also satisfying. Okay, let me, so this is for this, and you know this phi prime t is also f of phi. for all in the whole plane R, right? You know that these phi and psi satisfy this kind of differential equation. Now look at it this point. Consider this as initial value. So consider this system y prime equal to f of y, and y at some t naught is equal to this point is, let's say, y naught, so is y naught. Now when you consider this equation, you know that this has a unique solution y, so you cannot get two curve emanating from here, this point. This would, right, this would contradict Picard's theorem. So from one point as an initial value, you can expect only one curve which will go from that point, correct? So this is the kind of, I mean, this is the obvious reason why you cannot have two orbits which will intersect at a point. Okay, I hope this argument is clear, but this is not the proper proof, but this is the whole idea. You have to use the uniqueness of the solution. Okay, so this was the first property of this orbit. The second property is, suppose you have this kind of that suppose phi is a solution, okay, or phi is an orbit. So phi t naught plus t is equal to phi t naught. Suppose you have this. So t naught is any given point. So what it basically means, that suppose you are drawing this solution. So this solution is phi t, okay, and suppose this at some point t naught, this is the point what you have, and then this is saying that after some time t, okay, so let me draw this. So after some time t, so this is the whole time interval, this is the path traveled by phi t, okay, then it's saying that phi at t naught will be equal to phi at t plus t naught. So after time t, the point where you reach is basically this point phi t naught. Okay, so in 2D you can assume, you can clearly see that this is kind of a closed curve, right? Since if in 2D, right, in 2D this is a curve, the solution is a curve basically, right? And this condition basically means that it is closed at t naught, that kind of thing. Okay, we'll come to this later on, but at this point, suppose you have this kind of condition, okay, then what it say, that at each point t, it's not just about t naught, but at every point t. So suppose now you consider this point t, then again, so from here if you start, then again you will follow the same path. So again this phi t for each t is equal to phi t plus t. That means after time t, when you trace that curve, you will again reach at the same point. Okay, so you cannot, so what it says that, okay, suppose this is true, that at t naught, at this point you have this kind of property, but after this you cannot go from here like this, right? From here you cannot go like this, because at the other point, so suppose this is phi t, okay, which is t, some t naught greater than t, then after time t also you should return to this curve, and this is only possible when this kind of approach is there. That means it is revolving around in this closed area. Okay, so this is what it said, that if at some point t naught there is some periodicity at some single point, then it is actually a periodic function. Okay, so at a single point if you have some periodicity, so this t will be called the period of this function phi. So if a solution orbit, okay, has this kind of property that at some t naught and after the point time t naught plus t, if you reach at the same point, then for every t it will be having that periodicity. Okay, so this is another property that you have for this orbit. Okay, okay, and in 2D you know that this is what it closed curve kind of thing. Okay, and this is what is written here, that if you have this kind of property, then the orbit of this solution is closed, right? The graph of this solution will be closed. And the converse is also true, that suppose you have a periodic, that if the solution is periodic, the solution will be periodic if the orbit of the solution is closed curve and it should not contain any stationary point. Okay, so if you draw the curve, if it is coming to be closed and it is not containing any stationary point, then the corresponding solution yt, okay, is periodic. And I mean, it is clear from this graph. I mean, that's how this orbit is defined. Orbit is nothing but the graph of this yt, not graph, but okay, if you eliminate the t, that is the, I mean, the projection of the graph on this plane, right? Okay. Okay, so now again the same kind of definition, equilibrium point. This I have uh, already I said few slides back. So now let us see what is isolated critical point. Okay, so isolated is like, so it's like, suppose you have some point x naught y naught, and this x naught y naught is say critical point, then it will be called isolated if you have a neighborhood, maybe it can be very small. So if there exists a neighborhood around this point, then any point from this neighborhood cannot be critical point. Okay, that means if f of x naught comma y naught is equal to g of x naught comma y naught is 0, suppose this is true, if, then, okay, I mean, so okay, then f of x comma y and g of x comma y cannot be simultaneously, it cannot be 0 for all xy in some neighborhood n of x naught comma y naught. So if the function f and g are vanishing at some point x naught comma y naught, then that point x naught comma y naught will be called isolated if there exists a neighborhood in which the function cannot vanish simultaneously. Okay, so if it vanishes at x naught y naught, then there will exist a neighborhood where both cannot vanish simultaneously. So you know that this, for equilibrium point, you need to get this, both functions should vanish simultaneously. Okay, so this is what isolated means. So isolated means the point is living far from the other critical point. That is what we mean. So this is isolated in English terms. Isolated means keeping away from something. So here isolated means that you are a bit far from other critical points or other equilibrium points. Okay. Okay. Now let us see the definition of approaching path and entering path. So approaching path means, like, suppose you have an orbit, okay, that means a curve or path. Okay, then let us say that, okay, we are denoting it by, this is the parameterization how we do that, x coordinate is denoted by phi t and y as psi t. So we are in two dimensional, okay, and for most of the cases we will be in two dimensional only. Okay, so suppose you have this kind of parameterization, then 0 0 is critical point of 2, that means this system. But okay, the whole theory, what I'll say, I'll talk about 0 0, but this can be extended to any critical point x naught comma y naught. Okay, there is nothing very special about this x naught comma 0 comma 0. Okay. Okay, so 0 0 is critical point of 2, suppose it's there. Then we say that the path c or the orbit c approaches the critical point if this happens, that as t goes to infinity, it is going to 0, that means it is approaching 0 or the so suppose here it was x naught comma y naught, then here you just remove this x naught comma y naught at this point instead of 0 0. So here, okay, if I am writing 0, it is basically 0 comma 0. Okay, so if you talk about any other equilibrium point, you just remove that by this x naught comma y naught. Okay, so that's what I was saying, that there is nothing special about 0 comma 0. The same thing follows for any critical point. Okay. Okay. So it is called that approaching to 0 0 if as t goes to infinity you have this, or as t goes to minus infinity the curve approaches 0 0. So any one of them should be true. Okay, that means in other way, like if this is 0 0, then the curve should be like this. So maybe the arrow can be like this. So arrow represents t going to infinity. So this means t goes to infinity, this is approaching to 0, and as t goes to minus infinity, it approaches 0, means you will have the opposite sign, that means this side. Okay, we'll see, I mean there will be some examples that will be discussed where we will see how this notion is coming. Okay, so approaching means okay, it will approach the origin, okay, or any critical point, whatever critical point we are considering. The other thing is this entering path. Okay, so the path or the orbit c is called entering path. Okay, if the first thing is that it should obviously approach to the point 0 comma 0 or any critical point, and this ratio, what this ratio is, so suppose this phi t and psi t are the parameterization of this curve. So suppose this c is the curve, so in this xy plane this c is the curve, so this, okay, this is approaching 0, so okay, here I am just mixing the 0, but it's not like it is directly going to 0, but it's tending to 0. Okay, so the first thing is that it should tend to 0, that the phi t and psi t limit phi t and psi t should go to 0. This is the first condition, approaching path. And for critical entering path you need one more extra condition, which is the ratio psi t comma phi t, the ratio should also converge to some finite limit L as t goes to infinity or as t goes to minus infinity, any one of them. Okay, so what this is being represented, this ratio, if you see, so suppose this is some, sorry, so suppose this is some point phi t comma psi t, then this ratio is nothing but this straight line joining origin. This is something, it is measuring the tangent or slope of this curve at this point, right, at this phi t comma psi t. Okay, so this is representing the slope. Okay, so if this limit has also, this ratio also has a finite limit, did not be 0 but some finite limit, then we say that this orbit c is an entering path, so entering to origin. Okay, so it is, so when we say that approaching, that means it is tending to 0. In entering, like we say that it is approaching 0 in a proper manner. Okay, we'll see what that proper manner is. So that proper manner is basically this ratio is what is defined. So how this ratio is making sense of it. Okay, so maybe I should give some example for the more clarity. So we'll see, you consider this example. Okay, so this, okay, so when I'm writing this a, this is like I'm talking about this system. Okay, where a is given by this matrix. So we know in this case the solution is given by e raised to the power minus t, then you have here cos t minus sin t cos t, correct? So this is the solution of this system, okay, which represented by this matrix. In the same way, over here we have e minus 2t 0 0 e minus 2t. Okay, and okay, here you can put y0, here also you can put y0. Okay, now if you try to draw the orbit, okay, so then what you get is this kind of curve. So suppose this is y1, this is y2. Okay, so here you will get a spiral kind of thing. Okay, what you get is, so suppose you are starting with this point, so suppose y0 is 1 0. I'm taking a particular choice just to show how the picture will look like. So suppose you have 1 comma 0. Okay, so let me write here solution. So what the solution will be, e minus t, you will get cos t, here you will get sin t, right? That means suppose you now choose, so t you increase. So here I am talking about when t is 0. This point is being represented. Now after some point, so let us choose for our convenience t as pi by 2. Then what you get is at t pi by 2 you'll get, this will be e minus pi by 2, and this would be cos pi by 2 would be 0. Here you will get 1, right? So it would be somewhere here. So y1 component would be 0 and y2 component would not be 1 but less than 1. So here e minus pi by 2 is less than 1. So it will not be, so suppose this is the length 1. Here you will have length 1. So it will be a bit decreased. Okay. So you'll get this kind of curve. Again, if you do it further, so let me draw it more. So less than 1 is this kind of thing. Maybe. And again it will keep on decreasing. And it will be revolving in this fashion. Okay, and then it will approach to 0, correct? So here this diagram represents as t is positive. Okay, so this kind of curve. So now when you, if you want to get the solution curve, so this is the orbit corresponding to this initial, this is an orbit. Okay, so this is orbit. Okay, this is one orbit. You can clearly see it is not containing an equilibrium point, because the equilibrium point for this system is nothing but 0, 0, right? Is the equilibrium point, correct? This is the equilibrium point what we have. Okay, so it is not, so this is how. And if you want to see what this solution curve is, so you just add this t axis. So maybe you can add t here, then you'll see that it's like you started from here, it will go keep on increasing, right? This kind of thing, but the diameter or the radius would be decreasing, and if you project it, it will look like this. Okay, so this is orbit, this is the solution curve. Okay, so we have talked about the solution curve and orbit before, so now let us concentrate on the thing what I was trying to explain, which is what is the approaching path and entering path. So from here, okay, so this is one orbit what we have, and here you can see, that limit t tending to infinity, this yt is equal to 0, 0, because this is a bounded, these two are bounded function, and we know that this quantity goes to 0 as t goes to infinity, right? So as t, so here let me write t more precisely, t going to plus infinity. Okay, so as t goes to plus infinity, we know that the limit point is becoming 0, 0. So this is clearly an entering path. So this is orbit and this is an entering path. But the question is it, sorry, this is the approaching path, this one, sorry. So, but the question is it an entering path? This is approaching. Okay, now the question is it entering path? Now let us check the ratio. So if you try to check the ratio, let me shift it a bit. Now if you want to calculate the ratio, then limit t going to infinity, if you do y2t upon y1t, what you get is sine t. So limit, I don't know what has happened. So limit t going to infinity, and then this is, so e minus t will cancel out, so you'll have sine t upon cos t, and you know that this limit is, what is this limit? Will it exist? Sine t and cos t. So this is, what is this? So limit t tending to infinity, this is tan t, right? Do you know the value of tan as t goes to infinity? What is the limit? What do you think? It will not exist, right? Correct. So this does not exist. So this is not an entering path. Hmm. So, but not entering. Okay. So now let us look at this example. So here this is what we have. So again let us say uh, what initial data. You choose any initial data of your choice. So here let me choose 1 comma 1. Okay, or any one you can choose. So here you can see you will get e minus 2t, e minus 2t. Correct. So you can clearly see here x is equal to y. So the orbit is like this. Okay, it depends on what point you choose. So suppose I am choosing this point, then the orbit, I mean the solutions. So 1 comma 1 is this. So let me say this is 1 and this is 1. So this is the curve orbit, right? So as t goes to infinity, you can clearly see that the path is going to 0, right? Moreover, if you try to see the ratio, so limit t going to infinity y2 t by y1 t, if you see this is 1, right? So this orbit is an entering path. So this is entering path, right? Okay, so this is, so entering means it should go to 0 in a proper fashion. So here the slope is always 1, but here if you see the slope is continuously changing here like this, right? I mean, so if you zoom in, so this, if you want to calculate at this point, so this is the slope of the line connecting these two, so this is continuously changing, right? So that is why this is not an entering path, but this one is. Okay. Okay, now let us try to see some example or types of equilibrium points with some examples. Okay, so suppose you have a 0 0 as equilibrium point. Okay, one more thing, uh, here in the definition this ratio is concerning the point 0 0. Okay, that is the equilibrium point, but if you have some other equilibrium point x naught comma y naught, then you should consider this kind of so this would be y naught, and here you will have this kind of ratio. You should check the limit of this kind of ratio. Okay, t going to infinity or t going to minus infinity. Okay. Okay, then this was about this path. Now let us try to see what is how I mean how we can distinguish the equilibrium points. Okay, so there are few notions. We'll see that one by one. So let us start with this center. What is a center equilibrium point? So this 0 0 equilibrium point is called center if, so let me draw, so let me explain it by picture maybe. So this 0 0 is called center if there exists a neighborhood around 0 0. That means suppose this is the neighborhood, okay, which contains infinitely many paths Cn. That means it should contain many path, so C1, C2, C3 like that, okay, which contains interior, this origin is interior of each of the curve, okay, and the size should decrease. Okay, so there should exist a sequence of path, okay, which will, I mean the diameter will increase, decrease, okay, and okay, if you look from here to here, I mean the basically the idea is that any neighborhood if you consider around 0 0, it will contain many path, and all the path will be uh, I mean the size of it will either increase or decrease. I mean it depends on how you look. So if you are looking from this type, you will say that the size is increasing, and if you look from here, it says that the size is decreasing. So it depends just on the enumeration of the Cn, nothing else. Okay, so the main idea is that size should be converging to 0, or it should become very small and small. Okay, so this is how we define the center, that this equilibrium point 0, 0 is center if such thing happens. Okay, so let us look at this example, this one. So here we know that the solution yt is given by e raised to the power 0t, which is 1. So this 0, so this is 1, so we'll remove it, and then we have cos t minus sin t sin t cos t. Okay, this is the expression of the solution that we have. Okay, now let us try to see. You can clearly see that from here, that 0 comma 0 is equilibrium point. Okay, this we have already have. So now we have to check whether this 0, 0 is at center or not. Okay, so let us draw this phase diagram. Okay, so choose one point from here. So this is, let's say, some 1 comma 0, let's say. So I'm choosing this point. Now if I substitute it here, I mean here, then corresponding to this yt will be this cos t and sin t, correct? So the curve would be like this. It will be a circle. Okay, okay, so this is the curve corresponding to this. If I choose some other, if I continuously keep on decreasing the radius, right? So if I put here, so let's say this is c comma 0. Okay, then here I'll get c. Now if I continuously keep on decreasing the value of c, you'll get many concentric circles like this, right? So, right, so this kind of thing will be there. So you can see that whatever, so I mean I can decrease it further as well. So whatever neighborhood you choose of this origin 0 comma 0, so suppose this is some neighborhood of 0 comma 0, you can see there are infinitely many paths or orbits, okay, with diameter becoming very small and small, right? So this quantity, and each of them is containing origin as an interior, because here you can see they are just circles. So they contain origin as an interior, and the diameter of the path approaches 0 as n goes to infinity. So this is like p1, p2. So you can say instead of c, I can choose, let's say, 1 by n. So this c is nothing but 1 by n comma 0. You can see there exist, as n going to infinity, this path is becoming small and small. Okay, okay, so this is an example of center, how the center equilibrium points look like. Okay, we'll see some characterization also on the basis of eigenvalues. You can clearly see that this solution, how we write the solution. In previous sessions we saw how to write the solution, and that solution was being written using the eigenvalues. So at last I'll say something about how eigenvalues and this equilibrium point is related. Okay, we'll see that later on. Okay, so now let us talk about the saddle point. So saddle point is nothing but it is satisfying this kind of property. Okay, I mean explaining this using eigenvalues is much simpler, but let us see first the formal definition what we have. Okay, then we'll go to the characterization. So saddle point means that there should exist two paths, okay, two paths which approach and enter 0, 0. That means the path is an entering path, and the entering path is corresponding to the equilibrium point 0 comma 0, right? Remember this definition. Entering path for 0 comma 0 we have defined, but it can be done for any x naught comma y naught. But here we are talking about 0 comma 0. It's like there should exist two paths which enter 0 comma 0, okay, from opposite direction. Okay, so it should, if one is coming from here, the other should come from the opposite, this side. Okay, so it should be like this or this. So this should be the curve path. So this is the first condition. The second condition is that there exists two paths which approach and enter 0 0 from a different pair of opposite direction as t goes to minus infinity. So here I am saying that as t goes to infinity, the path should be like this. This is the first condition. The second condition is that as t goes to infinity, minus infinity, the path should go like this. So here we are talking about t going to infinity, and here we are saying t going to minus infinity. Okay, I'll explain through examples, maybe. I mean, it will be clear from the example. The third condition is, okay, let me solve this, then it would be easier to understand. Okay, so because this is some way, it's like, so let me explain pictorially, then it would be, then I'll go to example. So suppose this first condition is saying that you should have this kind of thing as t goes to infinity. So if you choose point from here, this should be one path like this, one path like this, the other path should be like this, going away from origin. So this arrow, basically when I give this arrow, this means as t goes to infinity. So as t goes to infinity, it should go like this, and so as t goes to minus infinity, it should go the other way around. Okay. And then these are the first what I just explained. The other, this point is saying that now you see these lines are making partitions of the plane. So this is, let's say, first partition, second partition, third partition, fourth partition, right? So that's what it's saying, that in each of the four domains, okay, between any of the four directions, okay, so that means in each of these four regions there exist infinitely many paths, okay, which do not approach 0 0, okay, but are asymptotic to these lines. That means the other curve should be like this. Okay, I mean, this kind of thing, that it will, so it will be asymptotic to these straight lines. I mean, what I have just said, this kind of thing. Okay, here also, if such things happen, then we say that this origin is a saddle point. Okay, now let us try to see this example. Let me first write the solution. So yt is yt is given by e raised to the power minus 2t 0 0 2t c1 comma c2 or okay, so this is the way how the solution looks. You can clearly see, like, if I choose this kind of direction, so let me first say this is y1, this is y2. Now if I choose a point from, let's say, if I do this 1, so let's say y1 is some 1 comma 0, so y2 I am making 0. Okay, so if I choose this point 1 comma 0, then you can clearly see that the solution is nothing but e minus 2t and 0, right? That means as t goes to infinity, this is going to 0 comma 0, and the magnitude of y1 is decreasing. That means the solution would be like this, right, as t goes to infinity. So if I choose any point here, then the solution would be like this, so it will be going in this way, right? In a similar way, if I choose some point from here, it will go to origin in this way. Now if I choose some point from here, you can see that the solution, so now suppose this is 0 comma some point, then you can see if I put 0 here and if I put some c here, I'll get 0 and c times e minus 2t, sorry, e 2t. You can clearly see that this is going to infinity as t goes to infinity. So this will go to infinity as t goes to infinity. So if I choose any point from here, it will go to infinity. Okay, and if I join it to origin, although it's, I mean, 0, I'm not, this 0 you can consider as a hollow point. Okay, 0 is hollow point. Then if you start from any point from here, it will go in this direction, right? So this is the path. In the same way, you can go from here to here. Sorry, in this way, correct? So you understood, these are the four asymptotics. Now each of the curve, you can see, you can choose the point. So suppose you choose this 1 comma 1 point. Okay, and you can see this will be e minus 2t, here will get e 2t. Okay, so the first, you can see, if you take this point, I mean, you can write that how this. So here what you got, y1t is e minus 2t and y2t is e raised to power 2t. So you can clearly see y2 is nothing but 1 by y1, right? And this is y1 y2 equal to 1. So you see the graph would be like this. Sorry, I missed that point. But suppose this is 1 suppose this is 1 comma 1. So this would how the graph would look like. Okay, this is the uh, graph for this kind of. So if you choose the initial point 1 comma 1, so it would be like, so how the arrow would be decided, like this way, right? So going from here like this, so from here it will go like this. Okay, so this is how you can choose arbitrary points and look how the solution is being mapped, how you can plot the solutions. Okay, so the rest of this point will also be plotted in this way. Okay, this, let me rub this off. I hope you understood what I just explained. So I mean, this is the kind of plot. So all these are asymptotics to these curve, these four curves, right? So this is how saddle points look like. Okay, now let us talk about the spiral point. Okay, so spiral point is like, the first thing is that, okay, so I mean, it should be defined for all t greater than t naught. I mean, in fact, this should be true for all of the things what we have said, but in these cases we are talking t is belonging to R. I mean, it is defined for a whole real line. Okay, because we are talking about both the limits, t going to infinity and t going to minus infinity. Okay, so the first thing is that every path, so it's called a spiral if there exists a neighborhood, okay, such that every path you choose in this neighborhood, okay, if this is a path, then it should satisfy this kind of property. The first thing is that it should define for all t greater than t naught. The second thing is that as t goes to infinity, okay, it should approach origin. Okay, and as same for, or if t goes to minus infinity, it should go to origin. So either it is going like, okay, so I mean, either it is approaching to 0 or going away from 0, that's all. So this basically means going away from 0 in some sense. Okay, and the third thing is that it should approach origin spirally. Okay, I mean, going like swirling around. And this is the kind of picture I think I mentioned, this kind of thing. Okay, this kind of thing, you see, this is approaching to 0 in this swirling way. Okay, and the same example is there. Okay, so I'll just mention how what this solution is. So you know that this is the diagonal term, so I'll get e minus t, and the rest would be cos 2t. So here it will be sine 2t, here minus sine 2t, here cos 2t. Again, you can, the way I mentioned here, you can draw the diagram and it will look like same. Maybe the direction would change. Okay, so that is possibility. So what I'm trying to say is like this. So suppose you have this curve, okay, this was the curve what was drawn here, but in this case now the arrow will, I mean, it will no more clockwise, so it's matter of clockwise or anti-clockwise. So how should I draw? So let me draw in this way. I So here we saw, just let me draw and then I'll mention what it would be. So here it would be like this. Okay. You can check this one by yourself. The main reason is the sign of this one. Okay. So here forget about this diagonal terms. It's of no importance about the rotation. But look at the sign of this quantity. I mean, you remember this kind of matrix I introduced, A, B, B. Here it will be, if here it is minus, then here it won't be minus, and A. This kind of thing. So it will depend on the sign of B. Okay. So in this case, since I have drawn, I know that here it is becoming as anti-clockwise, right? So it is going like this, anti-clockwise. But now if I change, so here it's, you see here it was -1, but in this case here it is +2. Okay, here you have +2. So that's why here instead of becoming this anti-clockwise, now I'll have this clockwise. So both is going to 0, but in a different way. One is anti-clockwise, the other, this one is clockwise. Okay, so that depends on the sign of this entry. Okay. Okay. Okay, now let us talk about node. So node is like, okay, so these are the main two properties. So it approaches origin as t goes to infinity, and it enters. So basically it is an entering path. So there should exist a neighborhood such that any path you choose, it should enter origin. Okay, the path should be entering path. Okay, and we have seen in this example when I was explaining you this kind of thing, the diagonal thing, right? So here you see this diagonal, but okay, when I'll come to the characterization, you see how the eigenvalues will impact. So all these examples what I've chosen is kind of from that eigenvalues characterization, these examples has been constructed. Okay, it's, so I'll tell about that characterization at last. So at this point, let us see how this example, how the solution looks like. So for this case, you have e minus 3t 0 0 e minus 3t. Here you will have yt equal to e 3t 0 0 e 3t. Okay, in both cases you know y1 is equal to y2. So I mean, it depends on the constant what c you are choosing, but in all the cases you will have a straight lines. Okay, it would be like this kind of, sorry. So depending on whether it is this one. So depending on if you are having this negative sign, then all this path will go to 0 as t goes to infinity, right? Because exponential of minus 3t goes to 0. But if you have this positive sign, then you will have this kind of relation. Draw with green. But in both the cases we know that both are entering path, right? This is for green and this is for black. Okay. So this is all about node, so it should be an entering path, that's it. Okay, now this I have already explained in the earlier session. So it's written again in the same way what I've just explained, so I'll just skip this part. Okay, I'll just say that you remember this diagram, that if this is the initial point and this is the curve, stability means that there should exist a neighborhood like this such that if you choose any point from this neighborhood, okay, so this is the delta neighborhood, then there exists, so for this epsilon neighborhood there should exist a delta such that if you choose some point from here, the solution should remain in this epsilon neighborhood. That's it. This is what a stability means. And for asymptotic stability, you know that this should converge to this, the orange line should converge to the green line. That's it. Okay, so this is what it's written. So this norm is the Euclidean norm, so phi t naught square plus psi t naught square. Okay, this kind of thing. Okay, and unstable means which is not stable is called unstable. Okay, so this is another classification of, so see, this was one kind of classification, that whether the equilibrium point is spiral, center, node, or this, what do we call, saddle point. Okay, so this is one classification. The other classification is whether it is stable or unstable. Okay, and you saw that stability or instability, we have already seen that it depends more on the eigenvalues, right, whether the real part is negative or the eigenvalue is negative. But this kind of node, and this is also depending on the eigenvalues, how the sign of eigenvalues is, we have. Okay, so that is much more depending on the eigenvalues. So all the classification, this stability classification or this stability, this node spiral thing, both of them are can be characterized using the eigenvalues of the concerned linear matrix. Okay, so I mean, when we are dealing with linear, when we'll go to nonlinear, again we'll see if we can use the linearized information or not. So we have already seen how to deal with the stability of nonlinear systems. So we linearize it, we see that if something is there, can we conclude about the nonlinear. In some cases we were able to do so, in some cases it was not possible, right? So in same kind of thing we'll study here as well. So now main focus would be to study this kind of property, whether the equilibrium point is node, spiral, or what kind of thing we have. Okay. Okay, so this is the characterization. Okay, so for 2 cross 2 system, so this is the kind of system we have, linear system, and we assume that this matrix, so A B C D, this matrix has determinant non-zero, that means they are invertible. Okay, so that 0 comma 0 is the only equilibrium point. This is the reason of choosing such kind of systems. So we have 0 comma 0 is the only equilibrium point. We know that the characteristic equation is given in this way. Okay, and because of this this characteristic equation, if we solve, we'll get two roots. Depending on how the roots are, we will characterize it. Okay, so let us see. Okay, so now consider the case when the eigenvalues are real, distinct, and of same sign. Okay, so they are real and distinct. In that case, this 0 0 is node. Okay, so for example, look at this one. Here we had the same sign, you see. Okay, but here we were having this, so this is kind of here we had the same eigenvalues as well. Okay, but let me see what is real equal. Okay, this is also a node, but I understood why we have mentioned it, because we are saying something about the stability and instability as well. So as of now you can see this is a node, and here also if they are real and equal, then also it is a node. Okay, and real equal, we have a node. Okay, but the point is here they are negative and here they are positive. So when they are negative we have asymptotic stability, and when positive we have instability. Okay, so you can see in this example. Okay, here we had real eigenvalues with distinct, I mean real and same, but here the sign was negative. Okay, and so this was stable, this black line stability. So the equilibrium point, okay, I should not write it here, but equilibrium point is stable in this case. In this case it is not. Okay, but they are nodes. So when we have a real eigenvalues, and if they are of the same sign, okay, actually these 2 points uh, can be merged here. Okay, so real and same sign. Okay, I think these two can be merged. Let me see. So if they are real and of same sign, that's good enough. Okay, so this, I think it can be combined with this. So real and of same sign. Okay, so you can forget about this distinct condition. Real and of same sign, then it is a node, and it will be asymptotic stable if it is negative and unstable if it is positive. Okay, the sign of eigenvalues. The second characterization is it should be real, distinct but of opposite signs. So you can remove this distinct condition, okay, because when we say that it is of opposite sign, that means that they are distinct, right? So we don't need to write this also. So real and of opposite sign. So remove this thing, then I think then it would look more better. So real of same sign, then we have node, and it can be stable or unstable depending on the sign of eigenvalues. The second says that they are real but of opposite sign, then we have a saddle point, right? So in this case, if you see this example, you see the eigenvalues are of opposite signs, right? So like it's one is increasing, the other one is decreasing, that kind of thing, okay. Okay, now let us come to the complex eigenvalues. So if the eigenvalues are complex with non-zero real part, okay, so the real part is non-zero, then we'll have a spiral kind of thing. You see this now you think, it will be clear from here itself. So suppose now you put this as 0, okay, that means this is gone, okay. Then in that case the curve would be just circle, right? If you have one equal, if you have one here, so this circle is becoming like this because of this thing, right? Because of this exponential, and this exponential is coming because of this kind of diagonal term, and this diagonal term is nothing but, if you calculate the eigenvalues, you'll get 1 plus minus 2i. So this 1 is nothing but the real part of the eigenvalue, right? To remember this, if a is alpha beta minus beta alpha, then the eigenvalues are alpha plus minus I to beta of this matrix, okay. So so these values what we have, this diagonal entries is determining, diagonal entries is determining whether it will be spiral or not. So when we have eigenvalue is non-zero, we have a spiral kind of thing, this kind of thing, because of this quantity, exponential quantity. And if eigenvalues is 0, then we have just circle kind of thing, this is center. So not a spiral but center, okay. Now the direction or this arrow how we put depends on the sign. If t, if this diagonal elements are positive, then it would be in the opposite way, that it is going to infinity, otherwise it will converge to 0 0, right? The second thing is, which is not of importance, what is the sign of this b. If it is positive, it will be some either clockwise or anti-clockwise, that is not important as of now, okay. But when you draw this phase portrait, so these kind of diagrams are called phase portrait, that, so right, so I mean collection of all the orbits, okay, this is the called phase diagram that you draw on this xy plane, okay. So when you draw this phase diagram, then the direction is important, but for saying that whether this is stable, a node, spiral, center, or a saddle point, you don't need to worry about the sign of this quantity of diagonal elements, okay. So this is what it says, what I just explained, that if it has non-zero real part, then it is a spiral. If it is a zero real part, it has, that means it is a purely imaginary number, then that is a center. That means the size will remain constant, because cos square plus sine square will give you 1, and that multiplied by the constant c will give you some specified radius. But if you multiply by exponential of t or exponential of minus t, the radius would keep on increasing or decreasing, right? Okay, so this was the characterization of this equilibrium point using the eigenvalues, okay. Okay, so now let us look at some exercises, okay. So let's start with this one, okay. So you have y1 prime is 2y1, so in matrix form you can write it as y prime equal to this 2101 y, right? Correct. So now from, so here it is 2102, correct. So now in this case you can clearly see what are the eigenvalues of this. So eigenvalue, if you want to calculate, it is just 2 comma 2 right. So these are real eigenvalues of same sign, that means it is a node, right? Real of same sign. Then you know, in this case 0 comma 0 is a node, right? And if you want to draw the this what do you say, face portrait, let us see how the face portrait looks like. Okay, so we have to draw the face portrait of this system. So far we know that it is a node, and we can say moreover that it is not stable. So I mean it is a node and unstable, right? Because they are of positive sign from here. Unstable if the sign is positive. Okay, but for our satisfaction, just let us see how the face portrait looks like. Sorry, yeah. Okay, so yt you can see, you can write it as e of at times y0, and now you can write e of at. How do you write a? So a you can write it as 2002 plus 0100, right? So this is the nilpotent matrix. Okay, so we have done this kind of analysis further, so I'll just directly write. So there is e2t, and then you have ent y0. This is nothing but e2t. Here it will be I plus n, and n square is gone. So you will have 1 t 0 1 y0, right? This is the expression we have. Okay, so in write e2t y10 plus t y20, and here we have y20. So this is the expression of solution. Now let us try to draw this face portrait. Okay, so now let us choose some point. Okay, so let us start with, let's say if I put y2 0 equal to 0, so let's say this is y1, this is y2, and now choose y2 0 to be 0. So y2 you choose 0, so that means we are at this point, y2 0 and with some y1, and you can clearly see the second component is gone. So we'll have e2t y1 0, right, and 0. So this means that this y1 will increase as t goes to infinity, and y2 will remain 0. So this kind of thing. So maybe if you want to draw the face portrait is like this. And now if you choose any point from here, again the similar thing like this. So I mean it will be like this going to this way. So okay, so origin is not included. Okay, so that you have to think, because you know if you start from origin you will stay at origin, right? Because that is an equilibrium point. So if you start at origin you will stay at origin. Okay, so this is there. Now let us see. So if you choose some point from here, okay, so what you have is, if you choose some point from here, that means y1 is 0, so you'll have e2t y1 0 is 0, so you have t y2 0 and y2 0. Okay, so you can clearly see that both the components are varying as a function of t, and if you plot it you will see that this y2, okay, this y1, sorry, this y1 is some t times y2, right? This kind of relation we have, although t is there, but we have this, we are not writing y1 as a function of y2, but y1t is equal to t times y2t from here, right? So I mean you can plot like it will be something like this. I'm just drawing it. These are standard standard face portraits, so I'm just writing it here. That means, and if you try to go backwards, if you start from here, then you will go like this. Okay, so the face portrait can be drawn in this fashion, like this. It will be like this, and some, okay, and this will be like this. To understand this, I mean, as of now, you can just think that if you choose some point from here, okay, you will see this kind of behavior, and you will see that if you start at some point here or any point from here, you will see it will intersect. So if you, let me write in this way, e2t you have y10 plus t y20, okay, and y20, okay. Then why I am intersecting with this y-axis? Because you can see this curve. So this y10 plus t y20, that is the first component, is becoming 0 for some values of t, right? Because you see y10 over here, I mean maybe I should take some particular graph. So let me draw it here. So I'm saying if you start from here, the curve would be like this, right? This is my I mean the claim. Why? Because this you see y1, y2, and the solution is yt is given by this is y10 plus t times y20, and here you have y20. Okay, so my claim is that it is cutting this y2 axis, that is the first component is becoming 0 here, right? Uh, this is like 0 comma some y2t, right? That means this component is becoming 0, correct? Okay, so here it is some e2, e raised to the power 2t is also here. So this y10 plus t y20, if you want to equate it to 0, let us see if it is true or not. T is equal to minus y10 and y20. You can clearly see this y10, this quantity is negative here, right? This is my y10 and this is y20. So y20 is positive and this is negative, so this time is becoming positive, right? So if this is the state, I mean the point at t equal to 0, that means at some positive time it will cut this axis, correct? So this is kind of explanation what I am trying to give you for this picture. Okay, but you can explicitly draw and you can see that the phase portrait will look like this. Maybe I think my arrow might be wrong, I believe. This arrow, I think, because it should match with this kind of arrow, I believe. Okay, I think, okay, yeah, because this is like this, it would be like this, just to match with this arrow. Okay, okay, you can actually check also. If you start it from here, it will cut this axis at some time, positive time, because here you see, here at this point y1 is, in this point y1 is positive, y10 is positive, but y20 is negative. Okay, that means this time is again positive, so at some positive time it will cut this axis. Okay, so the arrow would be like this. Okay, so this is the phase portrait, and in this case, this, you can see this is asymptotic kind of thing for this one. Okay, so this is unstable. You can clearly see that this is unstable, and the eigenvalues are what do we say, this is same and uh, of same sign, so that means they are node. So this is unstable node. Okay, so this one, where did I write this one, the first condition? Okay, they are real and of same sign. Okay, so these are nodes, unstable node, what I wrote here. Okay. Now let us try to look at this example. Okay, so again here you see this y prime is equal to 1 2 3 4. Okay, y. So we just need to look at the eigenvalues. What are the eigenvalues? Let us see. A minus lambda I, if I do 1 minus lambda 2 3 4 minus lambda equal to 0. This is lambda minus 4, lambda minus 1 minus 6 equal to 0. It's lambda square, and then you have 4 minus 4 lambda minus 5 lambda, and then you have minus 2 equal to 0. So from here you have 5 plus minus b square minus 4ac by 2. This is 5 plus minus 31 by 2, correct? So here you see this is, so lambda 1 is 5 plus root 31 by 2, which is greater than 0. Lambda 2, which is 5 minus root 31, this is less than 0, right? So these two eigenvalues are of distinct nature. So again, you can look at this characterization. Here both are real and of opposite sign, right? So that means it is a saddle point. So 0 comma 0 is a saddle point, correct? This is what we have. Okay. If you want to draw the picture again, I mean, here I have drawn, where did I draw this one? So see here the eigenvalues are 2 and -2, opposite sign. That's why this kind of curve was possible, this kind of thing, that one was increasing, the other one decreases, like this kind of thing, right? So the same thing can be copied there, only the maybe like this would be like this, more steeper here and less steeper at the other end. That would be the thing, but overall this would be the nature of the graph. Okay, this kind of thing you'll see. So I'm not drawing it again, but you can understand that this kind of graph you'll obtain here as well. Okay, at this point. Okay, now let us look at this problem. So here you have been given an arbitrary values of a and b. Okay, and you have to say for what values of a and b it will be a stable. Okay, so sink means stable node or focus. Okay, so okay, focus basically means center. This is like center, center or spiral. Let me think. Focusing. I think it is spiral, not center. It should be spiral, like focusing something, right? It is spiral. Just a name. I mean, you just have to find the condition. I mean, to make the eigenvalue. So you recall, for a stable node, what do you want? What do you want? So for node, you want first thing is that it should be real eigenvalue. Okay, and of same sign. But for stability, you need the sign to be negative, right? So for same sign basically means here negative sign, or let me write same sign. Sign would be negative. Okay. Okay, and for this focus, what do you want? You want the eigenvalue to be complex. Okay. Okay, so for this focus, what we need is, the first thing is it should be complex eigenvalue, correct? And the second thing is, for stability, you again need the real part of the eigenvalues should be negative, right? So this is what we need. Okay, so here stable node or stable focus, I should write it here, stable focus. Okay. Okay, so now let us try to look at the eigenvalues of this. So a is a minus b, b and 2, correct? So this a minus lambda I equal to 0, if I do, I'll get a minus lambda minus b, b 2 minus lambda equal to 0. So if I do it, I'll get lambda minus a, lambda minus 2 plus b square. So from here what I get is lambda square minus 2 plus a lambda, and then you have plus 2a plus b square, correct? So this implies lambda equal to 2 plus a plus minus 2 2 plus a square, and then you have minus 4 2a plus b square. Okay, correct, and then upon 2. So if you solve it, you will get 2 plus a plus minus, from here what you have is, if you expand it, you will get a square plus 2a plus 4, right? And here you have minus 8a, sorry, here you will get 4a, and here you have minus 8a minus 4b square. Now if you combine it, here you will get minus 4a, correct? So that means this is a minus 2 whole square minus 4b square. So 4b square, I am writing it as 2b square. Okay, and then upon 2. Okay, so this is the kind of eigenvalue, I mean what the expression of eigenvalues we have. So let me just copy. Okay, okay, so this is the eigenvalue we have. So let us look at the first one, that is for stable node. Okay, so recall that for a stable node we need real and negative eigenvalues. So the first point, let us make it for real. So what do we need for real eigenvalue? So for real eigenvalue we need this the term which is under the square root, we have to make this positive. So a minus 2 square should be greater than 2b square, correct? So this means uh, so mod a minus 2, right, this is greater than 2 mod b, right? So this is what we need for stable, I mean for the real eigenvalue. Okay, so now you can rewrite this one. So I'm just removing this mod. So from here what I get is a minus 2 is greater than 2 mod b, or minus of a minus 2 is less than 2 mod b, correct? So this is nothing but a greater than 2. Okay, I mean here you can put equal to as well, right, because it can be it, even if it is 0 you have a plus 2. Okay, so that is fine. So here you will get a greater than equal to 2 1 plus mod b, and here you will get what will be, so a, here you will get minus a plus 2. So a, sorry, oh sorry, here it would be, right, my mod I'll remove, I'll get this one, correct. So here I'll get a less than equal to 2 1 minus mod b. Yeah, okay, yeah, so this is what we get, correct. So this is for the real eigenvalue. Now you can think for negative. So for negative eigenvalue, so this conditions make sure that the eigenvalue what we'll obtain is real number. Now to make sure that this is negative, okay, you see here you have two eigenvalues. Let me write it distinctly. So you have lambda 1 equal to this with plus sign, and the other one is lambda 2 is this one. Okay, okay, so now you see that for negative eigenvalue, okay, so here it will be minus. So once we make sure that this is negative, suppose I have somehow putting condition, we make sure this is negative, then obviously this will be negative, right? Because here you are adding this, with this one you are adding some positive thing, right, this one. But over here we are subtracting something. So if adding something is making it negative, then obviously subtracting also will make this a plus 2 negative, right? So we don't need to care about this one, we just need to care about this first with positive sign, right? So here what we want to make sure is, for negative eigenvalue you have to make sure that this a plus 2 plus this root square thing, a minus 2 square minus 2b square is greater than 0, right? This means that a plus 2 should be greater than minus of uh, this a minus 2 square minus 2b square, right? Just a second, sorry, here it is negative, so this part should be negative. Okay, uh, just a second, okay, and this is anyway non-negative, this we have make sure from our part. So you can write here two things. So see, to make this negative, what you need? The first thing what you need, want to make sure that this should be negative, right? Otherwise, there is no chance of making this whole term negative, because you know that this term is positive, right? So to make sure this is negative, first thing what you want to make sure that this a plus 2 should be negative, right? And the second thing is that the magnitude of this one should be much higher than this one, so that this will dominate. That means the mod of a plus 2 should be greater than this thing, because this is positive, so we don't need to worry about the sign. So this mod, the modulus, should be greater than this quantity, correct? If we are having this property, then obviously this is negative. Okay, so this would mean simply that a should be less than minus 2. That is an obvious thing. Okay, and the second thing is what we come from here. So let us square this one. So you will have a plus 2 square greater than a minus 2 square minus 2b square. This would give you, so from here you will get a square plus 4 will cancel. So here you get 2a greater than minus 2a, sorry 4a, 4a, and here you will get minus 4a. So overall you will get 8a here greater than minus 4b square. This is a greater than minus half b square, right? So this is another condition on a. So these are the condition what we have obtained on a and b, right? Overall you see that there are two lower bounds. So one lower bound is this one, the other lower bound is this one, correct? So you have this one as the lower bound and this one as well. So let us try to combine all the things together. Okay, so here let us first see what this condition is making. So let me do one, this will make it. Here I have to remark one thing. Okay, so look at this point. So let me, if I combine this up, what I am getting is 2 1 minus mod b, just a second, just a second, a greater than, so here let's look at the lower one. So a greater than equal to 2 plus 2 mod b. Here I'm saying this. Okay, so let us, to be more simplistic, let us write in the combining this, what we get is a should be less than equal to minimum of the upper bound, that means minimum of 2 1 minus mod b and minus 2. Okay, the two upper bound, this one and this one, and it should be the maximum of the lower bounds. So here you have 2 1 plus mod b and then minus b square by 2, correct? So a should lie in this range. So a and b should satisfy this kind of bound or relation. Okay, if we have this kind of relation, then we are done. Okay, maybe you can try to simplify it further if possible, I don't know. Okay, but as of now let's write in the best way that we have this kind of thing. Okay, this is the relation. If we have, then we know that the eigenvalues will be real and negative. Okay, okay, so now let us try to look for the spiral. Okay, so for stable spiral, okay, for that what we need, eigenvalue should be complex with real part negative, right? This is what we have. Okay, so let us see for complex eigenvalue. So for complex eigenvalue, we want this term to be of opposite sign. So copy. So we want this thing, this should be there, right? So that means, okay, let me write it here. This is mod a minus 2 less than 2 mod b. This means minus 2 mod b, 2 mod b. So this is 2 1 minus mod b less than a 2 1 plus mod b. So this is the range of a what we should have. Okay, so this is for complex. Now for stability, oh sorry, for negative real part. So for negative real part, what we need is uh, so what was the eigenvalue? So this. So for negative, you can clearly see that when I'm making this negative, that is coming from to be as a complex number. So this is purely imaginary. So I times something would come. So for negative real part, we just need to make sure that this a plus 2 is negative, right? So for negative, a plus 2 should be less than 0. Okay, and this means that a should be less than minus 2. Okay, so this is a simple condition what we have got on a, and here we have got this thing. Okay, so now if I combine this, so you'll getting 2. So here you will get 2 1 minus mod b less than a 2 sorry, so minimum of minus 2 1 plus mod b, this one, correct? So this is the bound what we can obtain, but here you can actually simplify it further if you look at this one. Maybe just a second. So I hope that 2 1 minus mod b just a second. Just a second. Okay, this is what we can obtain, but here what you see, if you see at this condition, this one, let us look at this one, 1 minus mod b. Okay, now suppose that this b, so what I mean that suppose 1 minus mod b is greater than minus 1. Okay, then that would mean that this is greater than minus 2, but we know that a is less than equal to minus 2. So there is one more condition on b we can put, right? We should put, that is 1 minus mod b. Okay, 1 minus mod of b should be less than equal to 1. That means mod b should be greater than equal to, okay, sorry, mod b, am I writing right? 1 minus mod b should be less than, sorry, minus 1. So it is minus 1, minus 1. So here we get 2 mod b 2, this one, right? So here we got one more condition. uh, uh, so mod b, okay, so what I'm saying, so here we got, so from here we got this condition, right? That mod b should be greater than equal to 2. That means that 2 1 plus mod b, 1 plus mod b should be greater than equal to 2 into 3, which is equal to 6, right? So here this minimum value, would be minus 2, right? Because this is 6, so minimum is also always going to be minus 2. So overall the final condition what we can say is that a should be 2 1 minus mod b, just a second, so a should be lying between a and minus 2. Okay, so that's it. I mean, this actually you can ignore. Okay, so that's all. So you'll get this condition on a. Okay, okay, now this is a very simple exercise that I leave on you. Okay, it's not that trivial. You can clearly see that this yt is e lambda t 0 0 0, sorry, this will be 1. Okay, so you see this y1t is equal to E lambda t, and y2 t is always going to be 1. So if you want to draw the phase portrait, it's quite simple. Okay, so y1 t, you see this y2 is always going to be constant. So here if you do c1 c2, okay, so here you will get c2, here you will get c1. So y2 is always going to be this constant line. Okay, y1. Okay, so this y1, so you can see this as t goes to infinity, this is going to infinity. So y2 is always going to be constant, so this c2, right? So this y2 value is always constant. Now as t goes to infinity, this goes to infinity, right? This kind of phase portrait will have. And as t goes to minus infinity, so if you start from here, again t going to infinity, this will be like this. So this kind of phase portrait, simple thing, you can obtain in this particular case. Okay. Okay, so do you have any doubts?
This is okay.
Okay. Okay, then let's stop at this point.
And this actually last was having only one eigenvalue, right?
Where?
The last question, it has only one eigenvalue, right? Lambda.
No, 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 no. See, this is a 2 cross 2 matrix. That means it is having two
Oh,
eigenvalues.
okay.
And in this case, it is lambda
Okay.
and
That
0.
means. Oh, okay. 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 Okay.
Right? So lambda and 0 are two
Okay.
eigenvalues.
Okay. Okay. Okay.
Okay.
Okay. Thank you. Good night.
Okay. Bye bye. Good night. See you next week then.
Yeah.
Bye.
Yeah.